right? I think I might not told you, my first offer when I was in China is also a TSMC. So they gave me an offer, but I turned that down because I decided to come to the US to study, right? So there you go. Now that's another thing that we have in common, right? So today, I'm very proud of you, and I'm happy to see how you grow from someone who's knows nothing about materials, nothing about all the things here we do, become who's an expert now. I know there's a journal paper already on the preparation, right? So very happy for you, very proud of you. All right, so today we look forward to your presentation. So go ahead.
Thank you, Dr. Ling, for the introduction. I cannot believe how soon the day will be covered. So good day, everyone. Thank you all for being here. It's my pleasure to have this opportunity to present to you. Today, my topic is design and additive manufacturing of lattice polymer structure. So after today's presentation, in the near future, I'm going to accept a position in Taiwan. And after 2 years, maybe I can come to Arizona to compensate for the food that I owe you today. Okay, so I have divided my presentation into several parts. I will start with the introduction about motivation and background. And then I will talk about the experiment method. That is how we approach the CAD design and mechanical testing. Following will be a result, conclusion, and an acknowledgement. So to begin, I would like to discuss the motivation for this project and some background. In the past, most material used for production have been solid. There are, however, many studies that focus on improving the mechanical property by incorporating the lattice structure design. However, there is still not an efficient way for manufacturing products with such complicated structure. Recently, lattice structure has become a comparing topic because 3D printing provides an easier way for us to manufacture. So lattice structure is composed of an air and hollow structure, a ratio aligning with the different components that serve as support material. So as a result, a product that can utilize a lattice structure are lightweight, have higher strength and higher energy absorption compared to a solid material. So this combination of the properties gives these materials extensive applicability in various industries. So, for example, for unmanned aerial vehicle, we can use lattice structure to build the wings, which will decrease the weight and increase the fuel efficiency. In the medical field, we can use 3D printing to produce the bone implants, and because the lattice structure has high biological compatibility, allowing the blood vessel to grow in the hollow section. So there are many other examples of exciting application that for the sake of time couldn't be included in this presentation. Instead, I will discuss a unique lattice structure that I designed and studied during my graduate career in the UTEP. So beside vehicles and medical field, there are quite a few applications. You might already notice that in our life, such as these shoes or this tool. So 3D printing changed our life by producing items with complex structures that cannot be easily manufactured by traditional methods. For example, Adidas implements 3D printing to produce a sole of these shoes to increase the energy absorption ratio. In other words, it can absorb the impact from the face more efficiently. So this increases the energy absorption, provides more comfort for us to wear these shoes with this lattice structure. So besides allowing for increased structural complexity, 3D printing can yield a product that with molten material, allowing us to print hot and soft material simultaneously by making a hot offshore to prevent the deformation and the soft inside to increase the energy absorption of the material. So it will become like a sandwich structure. Printing with multi-material will be the interesting expansion for this project. But in here, which mainly focus on the structure design so far. So, an example of the structure design of metamaterial in this project is just like this door lock. So they designed several unit cells with varying harness, which allow the decomposition in a multiple direction. By rearranging these unit cells, we are able to manufacture a product with unique internal function. This is called mechanical metamaterial. Metamaterial will be the focus of my presentation today, and I will further define them in the following slide. So metamaterial is not a traditional concept that we think about the material. It's not actually a natural material element. It's more like the structure which is composed by a small unit cell. By rearranging the unit cell into a different pattern, we can obtain very distinctive properties, such as the ability to change the direction of the light path, like negative refractive index. But metamaterial is not only can improve the optical property, we can use the metamaterial to change the mechanical property as well. The picture in the middle is showing the effect of negative coherence ratio. We call it mechanical metamaterial. Mechanical metamaterial with negative coherence ratio can improve the shear modules of the material. So take this animation, for example, in the right corner. If you stretch it, in our normal experience, a typical material will get thinner. However, with the negative coherence ratio, if you stretch it, the structure will become larger of the side of the material. So beside of negative coherence ratio, there are a bunch of mechanical properties that can be improved by metamaterial design. As a result, in order to have a lightweight and strong material that we took advantage of unique features of metamaterials to give us mechanical properties that we are seeking. So in this slide, I would like to talk about the enhanced design of lattice structure. This is the basic theory of our research. That's how we use lattice structure to enhance or improve the mechanical properties. So in the past, the sandwich structure is able to provide a high toughness and a high energy absorption ratio. Sandwich structure consists of a core, which is a low density material, meant to absorb the external impact, and the plate on the top of that bottom, which is used to uniformly spreading out the stress or the strain to the core. The core can be bone, can be truss structure. So we choose the truss structure because the two components of the truss, the joint and the strut. So it's more intuitive for us to design within a pattern. So we can manipulate a design aspect to control mechanical property of the tooth by design a different pattern like stretch dominating or bending dominating pattern. The criterion to distinguish the pattern that is stretch dominating or bending dominating is by the connectivity. So if the joints connect with both struts, the pattern belongs to the bending dominating, and the stress will focus on the joint when the structure under loading, which will happen the rotate behavior in this part. And this mechanism makes the structure has higher energy absorption. So it will not connect with 6 struts. It's stretch dominant because there is one strut in the middle of the pattern. So the stress can be uniformly divided into a round. And because Because of this mechanism, the stretch fundamentally often have higher strength against the deformation. So by this unit cell design, we can use a fundamental arrangement to design a soft unit cell and a hard unit cell with a stretch dominating arrangement. Okay, so we improve the sandwich structure design on the core section and abandon the outer of the sandwich structure, which means we didn't add the top and bottom bedsheet to our structure design, and the whole structure became like the cellular metamaterial structure. So in the beginning of the CAD design, we are inspired by the metal crystal structure such as FCC and BCC. There are 5 elements in each. There are 5 elements in each face of the FCC. One of them located at the center of the face. That's why it's called face center cubic. And we translate FCC into a CAD file with a 2D coastline like the pattern showing. And as for the BCC, the frontend of the BCC is body center cubic. There's one element exists in the middle of the structure, and we use a 3D coastline to simulate that. So FCC and BCC have a different slate plan and different atomic packing methods. So they have different kind of deformation mechanisms when they are on the load. So the picture shows the deformation of the FCC metal. So FCC metal has a slate system on 111 plane. As a result, you can see the cubic in the right corner. We anticipate the deformation will follow the slate plan, which seems like follow the diagonal line. We are quite low. So in the following session, I will discuss how we incorporate the metamaterial design to improve mechanical properties. So while there are numerous design within the current research for metamaterials, I will discuss the unique benefits of particular patterns that are chosen in this project and the properties obtained from the design. And I will then talk about fabrication and how we manufacture our final product by 3D printing. Following is the result of the part. I will discuss the result of the mechanical property and performed by metamaterial design, and analysis the results of stress element from the compressive testing. So about the CAD design, we use a SolidWorks to draw this 3D pattern. We follow the standard that I mentioned in the previous slide. We design the FCC and BCC structure with the crossline in 2D and 3D pattern. Design of these two structures, we combine BCC and FCC cubic as a bigger cubic, and then uniformly divide the cubic into a smaller unit cell, becoming a BFCC cubic. So the length which we design for BCC, FCC, BFCC unit cell is 5 millimeters. After designing the pattern of the unit cell, we duplicate the cubic 5 times, become 5 by 5 by 5 on metal material. In this table, one row code IPF here. So IPF is atomic packing factor, which is mean the number of the atoms in per unit cell. And it's reasonable to our original purpose that IPF is correlated to a density. So literature shows that the strand will have positive ratio with density. And if we don't consider the number of the system initially, the FCC has highest atomic packing factor, and therefore the highest density. It is predicted to have the highest strength. So in here, I also write down which kind of different category of metal, like iron belongs to BCC, and aluminum, and silver or gold belong to FCC, and which often have higher strength because they're less sleep resistance than FCC structure.
Okay, so the poster size is 13 by 19.
Well, about the fabrication.
Size is 25 by 14. Okay. No, it's okay, it's okay.
So.
Yeah, I'll get back to you later, like in an hour or something.
Okay. So about fabrication, with development of the additive manufacturing, there are several kinds of 3D printing technique that we can use right now. So we choose to use the SLA printer instead. It's because SLA uses UV light to cure resin, which can have a better quality of the layer thickness resolution. So accordingly, the product that's built, that we build with will have a higher uniformity. So we can obtain a better mechanical properties than other 3D printing. And the benefits from SLA printing is that the print item is attached on the plate. So it's allowing for printing without the need for internal support. So we can save a lot of time during the post process because we don't have to remove the support material if it's inside the structure anymore. While there are many types of resin available, we choose to use the top resin for this project. It's because its final product is similar to ABS plastic. And because of the high tensile strength and high elastic modules of the top resin, they can tolerate more energy from the deformation and increase the area under the curve of the stress diagram. By this way, we can study more information about the stress and the strain performance. So this is the fabrication process. SLA is relatively simple and convenient for us to use. To begin, we just need to import a CAD file and set the parameter of the support material. And the support material the software will automatically generate the support material by itself. The next thing is that we set as 50 microns. And we need to add 2% to 1% of the support material outside to ensure the printing process is stable and in case falling down from the build plate. After printing, we remove the product from the build plate and remove the support material by this tool. After that, we wash and soak into a solution, which is isopropyl alcohol, for 20 minutes to get rid of the resin from the product. After cleaning, we use a Q machine to post-cure the product under 50 degrees Celsius and expose the product under the light with 405 nanometer wet band for half an hour to make sure the product will be total solidified. So for compressing testing, we use an instrument compression fixture following the ISTM standard number B1621 to tell us the mechanical properties of this product. So we can get the stress diagram in a compressed testing. From this curve, we can calculate the Young's modulus, which is the slope of the first curve, and the toughness, which is the area under the curve. So as I mentioned earlier, the anticipated deformation will follow the slate plan. More specifically, BCC will follow 110 and 211 and 321 plan, and 111 plan for FCC qubit. So from the first picture in here,
他可能就是跟刚才那个，
in
就是
here,
小孩突然叫那个，
we can see the
常
BCC
看到
slate
什么
plan is
Dr. Bill 的视频配的，
对啊，然后我就在那边。
is just like that, following a diagonal line. So because the slave system is made up by the plan and duration, we can calculate the slave system by multiple plan, and we will get a different value of the slave systems. It's very straightforward to think the number of the slave system is correlated to the strength of the material. So BCC and FCC are the same value of the slave system, and because BCC is a structure that we create in this project. So there is no data in previous literature as a reference. So from this table, it's very hard for us to understand which pattern will be stronger. So that's why we will do the compressed test and error and do the simulation.
有也蛮不错
真的哦。
才30几岁的郑教授。
So maintaining a steady compressive rate is crucial because the feature is not really fixed to our sample. Any acceleration of loading will affect the data of the stress diagram. For example, the tilt from the top plate will sense during the compressive testing if we apply acceleration, which will make our product, which will make our
他常说
data not accurate anymore. As a result, we program to
用中
the compression picture to maintain a same velocity. So the velocity we set is 1 millimeter per minute, ending when the total deformation equals to 40% of specimens of original length.
你好帅。
So as these three pictures showing, after the testing, the deformation in the difference in the deformation mechanism between them is not obviously through our visual inspection. In general, we can categorize FCC as bending as being stretch dominated, making FCC as hardest qubit among them. And BCC can be seen as a bending dominated pattern. The deformation are very uniformly divided into a whole structure. So BFCC is not a symmetric structure of the unicell. That's why BFCC will have a distorted deformation, like this picture shows. In other words, the Young's modulus of the qubit is correlated to its density. And after the first testing, we saw that the speed of the recovery was correlated to the shape that we used to and not related to the density. So we conduct a second test with the same parameter, discovering that the toughness increased by a different ratio with showing which is showing in the diagram in here. So after unloading, it's theorized that the sharp recovery occurs because the strength hardening mechanism in the polymer. So it is the strength hardening mechanism that increases the Young's modulus and the toughness. And we visualize the sharp recovery ratio versus to time in this diagram. So in here, you can notice that the fastest sharp recovery happens in the BCC structure, then FCC and BFCC qubit. Besides of these patterns, we had one experiment before to test the different size of the unicell. In general, we understood that the smaller unicell just needs to recover a small ratio of deformation after the completion. So coming back to the diagram, we use the assumption to explain why BCC recovery fastest, which is because the deformation will focus on the joints in a whole structure. So which means the deformation will be uniformly divided into different layers. By this mechanism, BCC pattern just need to fix the smallest part to recover its shape. That's why we think it's recovering the shape reflectist. And about the BFCC, because they are non-symmetric pattern, which would collapse two layers at the same time, because that have highest degree of deformation. That's why the strength hardening increased largest ratio of the toughness in the BFCC structure. Okay. So in the end of this project, we use FES simulation to validate the deformation results and to have some further understanding to deformation mechanisms. So in the beginning, we set a fixed corner to make sure the structure cannot be moved and apply the deformation loading with 1 millimeter per minute velocity, just the standard setting of the compressive testing. So the simulation of the unit cell are showing in the right corner, in the right-hand side. There is no significant difference between the FCC and BCC structure when we are under loading. And however, when under loading, the stress will focus on the corner of the unit cell of BFCC. We consider that this is a reason that BFCC happens distort formation. Then we use the same parameter to do a simulation for metamaterial structure. So in the end, the simulation results showed us most deformation happens in the BFCC, which increased about 2.24% of the deformation. And the deformation in the BCC and the FCC are collapsed uniformly, not like how we anticipate. We'll follow the 110 or 111 plan. So we observe this lowest elastic strength intensity in the BCC, which are reasonable to account for the shape recovery speed, because the shape is uniformly deformed, and that can very efficiently spread out the energy into the deformation and recover it. So after getting this experiment results from metamaterial project, we were motivated to apply advantages to see maybe we can apply this merit to other projects. The piezoelectric material last mode are made by piezoelectric ceramic. So the mechanical property are hard and cannot be bended. And we think because the metamaterial can be used to control the deformation mechanisms and increase the toughness. So it has high potential if we can apply the metamaterial design to increase the toughness of piezoelectric. Especially we can use a combination of them to print the bendable piezoelectric material. So 3D printing torad piezoelectric composite has its own challenges. We attempt to use an SLI printer to combine the piezoelectric and metamaterial. But the limitation of the material which can be printed by SLA machine makes us tend to use the FDN to conduct this project. So this is the FDN printing method to fabricate our piezoelectric composite. To begin, we dissolve the PLA powder into DMA solution. After the PLA has fully dissolved, we blend in the solution with a functional light video powder to give us the raw material we would like to print. After uniformly blending, we remove the liquid by placing the mixture into a furnace until it's fully dried out. and then we cast the FDM filament through the extruder. So in this step, we test several temperatures to find the build point of this composite. So in the end, we found 190 degrees Celsius is the perfect temperature. If the temperature higher than 190 degrees, the material will become like too liquid-like and hard to ship. And if the temperature gets lower than this point, the material will be non-uniformly blended. So after printing out the plate-like product, we did the pulling process under 1200 volts per millimeter for 6 hours to obtain the dipole effect in the sample. So the pouring process is demonstrated beneath this slide. And before pouring, the dipoles are arranged randomly in the piezoelectric material. They will point to different angles of the direction. After pouring, they will align toward the same direction. As a result, the dipole will gain a polarization, and if there is any deformation, the current will coming out from the material. So in the end, we had a good composite with 0.3 kilocoulomb per Newton of the piezoelectric constant. While this value is significant, smaller than the piezoelectric constant by piezoelectric ceramic, this particular composite proof that is very easy to print. So in the future, we still have a lot of things can do to improve the property of the composite. Okay, so in summary, metamaterial structure like BCC, FCC, PFCC was fabricated and tested in this project. And FEF simulation was used to validate the deformation mechanisms. And we tried the different piezoelectric composite formulas to fabricate a better composite. So the dielectric coefficient, the BCC coefficient, we got from the composite is 0.3 kilocoulomb per Newton. So in the future work, we can investigate the crystal structure by XRD to confirm that the strand hardening behavior is happening because of the polymer chain. And we can try a logic pattern to determine whether the different structure will have a different behavior. Because of the composite we met before is hard and brittle, we could try to use a different solution to function like filter powder, or to use a different solution to blend them together to make the blending process more uniform. So we are working on publishing the paper related to this project. We already finished a paper that we are writing on, and there are still some parts waiting for us to polish. So after that, we will resend it to advanced material to review it again. Okay, so in the end, I have to say thank you for your all to attendance. My deeply gratitude goes first to my advisor, Lee, for his careful guidance of my thesis in this semester. As an international student, there are so much problems that waiting for me, like language barrier, like the culture difference. So he taught me a lot of his experience about how to conquer his difficulties people. So helping me to understand how to survive in here. And I also thank to Dr. Zed who given me selfish help and support in my 2 years of development. So I'm very glad to have you be my co-advisor. You are the one best teacher I have ever met, and there are many good merits that I should learn from you, like kindness or selfless. And I know your time is more valuable than mine. So I especially appreciate Dr. Angel Oris about to taking your time being my committee to attend my thesis defense today. So thank you to I also thanks to my team member who have given me care and support in the lab. Because of you, my university life is more easier.
他在 thank you 他的那个 professor。
The last my thank will be go to Louis Travers. Though Louis is not here now, I deeply appreciate that the help from him for last 2 semesters. Gave me his help and time to listen to me and helping me working out my problem during the experiment. So that is pretty much of my presentation. Is there any question?
好，可以离开了。
Thank you, Gao. Good job.